Hi grade 12s, you're going to be looking at a couple of ideas in this class, the first of which is finding the area between curves. So last lesson we were looking at the area underneath the curve between curve and the x-axis. Today we're going to be looking at the area between the curves first of all. So if we were after this area A between the curve f of x and g of x, it's clear that if we took all of the area below this purple curve right the way down to the x-axis and then subtracted the area below the red curve, we'd be left with the blue area. Okay, so one way of finding the area between the curves is to find the integral, the definite integral for f of x, and then subtract the definite integral for g of x, and that will give us the required area A. What we tend to do though, because it involves less integrating, is to find the definite integral of the first curve minus the second curve. And what that sometimes allows us to do is a little bit of simplification before we integrate. So it can just mean that we're having to integrate fewer functions. So that's something one of the things we're going to be looking at this lesson. What we're kind of generating here is a function that is the difference between the two functions. So it's almost as if we're creating a third function which is plotting the difference for each x value between the two y values. So let's take a look at that quickly here. So if we are to sketch these, let's take a look what they actually look like on our calculator first of all. So we want square root of x plus 2, and we would like 1 divided by 2x plus 4. Okay, so this is what they're looking like, and we're trying to find the region enclosed by these two curves and the line x equals 3. So let's make a little sketch of these. Okay, so our first curve looked a little bit like this. Y equals square root of x plus 2, this being negative 2. And our second curve, let's take a look at that, was the bit that we're interested in really is over here. Okay, and we're also interested in this line. Okay, I probably haven't drawn that quite as accurately as I'd have liked, but this must be the region that we're looking for. So clearly this intersection point is quite important because that is the start, that's the kind of lower boundary of our definite integral. So to find this area, I'm going to take my function on the top, which is the blue function, and I'm going to subtract it from the function below. Looking at these, I'm not really going to get much in terms of simplifying by doing this. So perhaps this might be one which we can get our calculator to do some of the work for us. So I'm going to do the blue function, x plus 2, minus the red function, 2x plus 4. And obviously I need to think about these boundaries. So upper boundary is straightforward, that was given to us. The lower boundary, I can find it's the intersection of these. So let's find, oops, where's my calculator gone? Let's find this intersection. So we tap on here, we go function intersection, there we go, negative 1.37. Okay, and for my sketch I might add that, negative 1.37 and 0.794. Okay, that looks like a sensible thing to add to my sketch. Okay, and I'm going to get the calculator to find this. We can do this on this screen. So I can go into function signed area. I want to go from this value that we've already found, that's the intersection point. I want to go below function 1 but above function 2 rather than just down to the x-axis. And I want to go to, my upper boundary is 3. So, oops, 3. Okay, and looking at the diagram, it's quite useful because it shows us that, yes, we have got the area that we wanted. And there we go, roughly equal to 6.08. Now, you could have done that calculation on the home screen, that would have been fine. You could have done the calculations to integrals, that also would have been fine. So, where does this not work? It works if your upper function is above the x-axis, your lower function is below the x-axis, if they're both below the x-axis, if they're both above the x-axis. The time when it starts to fall apart is when they are doing this, when they're kind of switching which is above and which is below. If we took this purple curve as our upper curve and we're subtracting the black curve from it, we would get a positive area here. In fact, let's put plus signs there. So we get a positive area here where it's above the black curve, but down here it's below the black curve, so we get negative areas, and we get negative areas there. And if we were just doing this on our calculator, it could be that these cancel each other out and we get an area of 0, which would highlight the issue. Could be that we get a negative area, which would highlight the issue, or more sneakily, we might have functions where we get a positive area, and so we don't realise that we've got this issue. So when they're doing this, it's important we use the modulus symbol. Because what this is doing is it's saying, I want to create a function that is the absolute difference between them. So when we're doing the purple function minus the black function, rather than getting negative differences, we'll take the absolute difference. And so we'll get positive areas for all of these sections, which is what we want. So for this example, we've got y equals sine x and y equals cos x. So to find our area, we're going from 0 to 2 pi, and we would do the absolute difference. Sine x minus cos x. And in fact, that will give us the same answer as if we had done cos x minus sine x. It doesn't matter which way around they go now because of these absolute values. So the second part of this lesson is looking at the area between a curve and the y-axis. So before we were looking at the area between a curve and the x-axis, and we talked about lots of these vertical rectangles, and we said the smaller the rectangles are, the narrower the rectangles are, the closer it approximates the excuse me, the closer it approximates the area we're looking for. And we said, well, each of the rectangles is dx wide, and its height is whatever the y coordinate is at that point. And so we were adding them all up, which led to us finding the integral of our function. What we're doing now is we're looking the other way. Let's draw a slightly different curve. We're looking this way. And obviously it's the same idea. It's just our rectangles are going to be going horizontally. And now they're all going to be delta y tall and x wide, the x coordinate each of these points. And we're going to want to add these all up, and these are going to lead us to this. So that means having x as a function of y now, rather than y as a function of x. So let's look at what that means. So let's take a look at this example. By all means, if you want to pause the video, read what we have here, read the notes, please feel free to do that. It's the advantage of a video, isn't it? Find the area bounded by this curve, these values, and the y-axis. So let's think about what's going on here. Think about how we're going to draw this as well. So if I want to draw this on my calculator, I need to be able to have it as y equals x, some function of x. So clearly that's going to involve square rooting it. So let's see what happens when I square root 1 minus x. I get this. Now, the trouble is, when we square root something, we also have to remember it could be a positive or a negative. So I'm actually going to have to plot this in two parts, because this is only half of the curve we want. So I'm also going to have the negative version of it. Okay, so this is what it is. It's a parabola. It's the wrong way round from what we're used to, but it is a parabola. So we're looking at a parabola like that. Okay. Let's just check this. There we go. And we're looking from y equals negative 1, which is here, to y equals positive 1, and the area bounded by our curve, the lines, y equals 1 and negative 1, and the y-axis. So we're looking for this area here. Okay, so we're going to do this, but where we would be writing y's, we're going to be writing x's. So I'm going to go from negative 1 up to positive 1. I need a function in terms of y. So let's rearrange this. It's going to be x equals 1 minus y squared. And I'm integrating with respect to y. Notice my variables match up there. Okay, so let's integrate. Oh, actually, we could get our calculator to do all this, but let's do one without for a change. I'd get 1 minus a third y cubed, just the same as normal. Increase the power by 1, divide by the new power, and of course we put our limits in. Okay, and then let's substitute. So upper limit first, 1 minus a third times 1 minus negative 1 minus a third times negative 1 cubed. It's going to be plus a third. So I get 2/3 minus negative 2/3. I get 4/3. Notice I haven't bothered writing the plus c's in here. And you remember the reason why is that we'll have c minus c. So they just are going to cancel out. Okay, very similar to what we were doing yesterday. We're just looking at it from kind of a different angle. Things to be careful, making sure that you're rearranging and you're thinking carefully about what your function looks like. And making sure that your boundaries are y boundaries. There's example 4, definitely worth having a look at. I've put up the two different methods that I would consider using. One method is this kind of approach, finding the area between the curve and the y-axis. The other is a subtractive method. But definitely work through example 4 and think carefully about each of the elements we had here. A function in terms of y and boundaries in terms of y.